I have these ball launchers that I use in lab. You may have seen something very similar to them. It's basically a tube. You push a ball back against a spring, and then when it's released, the spring pushes it forward. And a student asked a question, and I've thought about this before too. And the question is, if we measure the velocity that it's launched as you shoot it horizontally, is that the same velocity if you shoot at an angle? And I always say, yeah, mostly, okay? But it couldn't be exactly, right? Because if there's a spring pushing this, and if it's going up a little bit, even though if that's a short distance, then there's going to be a change in gravitational potential energy, which would be a smaller change in kinetic energy. So in theory, it should matter, but in practice, it doesn't matter. That's the question. So I decided to go ahead and measure it. And I'm going to show you this launcher in just a second. I wanted to measure the velocity at a bunch of different angles in a simple way. And so the simplest way is to launch it and measure the distance, because it's easy to measure the distance using carbon paper, just letting it hit a different carbon paper, and you can measure all the dots later. And it's easy to measure the angle. But the problem is that the way the launcher is mounted, it's not mounted at the same level it lands, so you have this starting problem where it launches down here. So what I want to do, I'm gonna show you my data. I'm going to derive the velocity based on just the starting height and the final position, and then analyze the velocity for two different launchers, which I've already collected the data. Okay, but I'm going to show you this derivation. So let's go over to here. This is a video. So here is the ball launch. Actually, I'm using this ball launcher right here. Here's the smaller ball launcher. This is the I think this is the Pasco one, and it shoots it. Is it Pasco or Vernier? I'm not sure. And it shoots it horizontally, and it lands on this paper. And if I put a piece of carbon paper over it, then it'll leave a little mark. So here's a shot at an angle, and it's not that exciting. And there's the ball. You can see where it landed. And then I pick up the ball and I do it again. And I do it for this launcher right here and that launcher. And so my height is just this distance above the table. And then I measure the distance that way. And so I want to measure those two values for different angles. So how do you do that? Okay, so let's jump back here to the paper and derive that expression. So I'm not going to give a complete projectile motion tutorial. I'll assume you're somewhat familiar with that. The key thing here is that if I launch this at an angle, then I guess I am going to. I have V0x, I have V0y, I have V0 an angle theta. And so V0x is V0 cos... This chair. I don't know what's wrong with this chair. V0 cosine theta. And V0y is V0 sine theta. And then in the x motion, once the ball leaves the cannon, the launcher, it has a constant x velocity. So I can write x equals x0 plus the x velocity, which is v0 cosine theta t. And then there's no acceleration, so I don't have to worry about that. This chair keeps falling down. I'm going to switch chairs. Hold on. Don't leave me. It's really weird. Okay. So if I know this starts down at x0 equals 0, because it starts at x equals 0, and I measure x, I could find the velocity v0 with the angle, but I don't know the time. So I really get x equals v0 cosine theta t. But in the y motion, I can't get the time, because in the y motion, I have constant acceleration. It starts at some initial height y0 and ends at 0. So I have y equals y0 plus v0 sine theta t minus 1/2 gt squared. And again, the final y is 0, so I get 0 equals y0 plus v0 sine theta t minus 1/2 gt squared. And so if I want to find, that's a g. If I want to find the velocity, I actually can solve this equation for t and plug it in over there. I can't do it the other way around, because here I don't know v0 and x, right? Here, actually, I still don't know v0 and t. But I do know that if I solve this in terms of t and plug it in over there, then I can solve for, is that what I'm doing? Yes. Then I can solve for v0. So I actually have two equations, two unknowns here. Remember, I measure that, I know that, measure that, I know g. The only two things I don't know are t. So let's do that. Let's solve for t. So this is a quadratic equation. I'm going to write it in the form of 0 equals c plus bt plus at squared, right? That's your quadratic equation. And then in that case, let me get a new piece of paper because you know this is going to be a mess. I'm going to move that off to the side. So I have, let me write down my two equations. I have x equals v0 cosine theta t. That's terrible. And then I have 0 equals y0 plus v0 sine theta t minus 1/2 g t squared, because the y acceleration is negative g. And so this is c, b, and a. And I know that t is going to be negative b plus or minus the square root of b squared minus 4ac, all of that over 2a. So let's go ahead and do that. So this is a, negative g over 2. That's b and that's c. So t is going to be equal to, so I already know, okay, I've already done this problem. So I'm going to go ahead and say the minus sign is the one I want, because I'm going to get a negative b minus this term, and a is negative 2g. So this on the bottom is negative g. So I'm going to get all these negatives are going to be canceling. So I'm just going to get positives, and that's going to give me the right time. So I'm going to put in I'm going to write this as actually b plus the square root of b squared minus 4ac all over negative 2a. That's I factored out the negative sign. And I'm going to use the negative sign. Okay, so I get b is this v0 sine theta plus the square root of b squared, v0 squared sine squared theta minus 4ac. Okay, so a is negative g over 2. So 4a is going to be 2g. And then I have to multiply it by this. So it's going to be plus 2g y0. And then I have to divide all of that by negative 2a, which is just going to be g. So that's my time. Okay, so now I want to solve this for v0. So v0 equals x over cosine theta times, t. Is that right? Yeah. X equals v0. Oh, let me put it like this. Let's solve this for t. So t equals x over v0 cosine theta. Now this t and that t have to be the same, so this has to be equal to this, which is going to be v0 sine theta plus the square root of v0 squared sine squared theta plus 2g y0. All of that over g. Well, what to do next? First thing, let's get rid of that g. So I'm going to multiply both sides by g, and then I'm going to subtract this from both sides. So I want to get the square root by itself. So if I do that, I get xg over v0 cosine theta minus v0 sine theta equals the square root of v0 squared sine squared theta plus 2g y0. Remember, I'm trying to solve this for v0. Everything in here I know but v0. So the next thing to do is to square both sides. So if I square both sides of the equation, I get some messiness for sure. Okay, this is not why we don't normally do it this way, right? Because it's messy. So if I square both sides, I'm going to write it right here. Then I get x squared g squared. I'm going to get this term squared over v0 squared cosine squared theta. I'm going to get this times that twice, right? Because that's what happens when you factor. So minus 2 xg v0 sine theta, all of that over v0 cosine theta, and then I'm going to get that squared. So it's going to be plus v0 squared sine squared theta. And now on this side, I square that's pretty easy. v0 squared sine squared theta plus 2gy0. Okay, we actually can get a little lucky here because a couple things. Number one, this term's on both sides. I can cancel that. Over here, I can cancel those v0s. So now I get, push this up a little bit, x squared g squared over v0 squared cosine squared theta, and then I have this term minus 2xg sine theta over cosine theta. I'm going to write that as tangent of theta equals 2gy0. Now I only have one term with v0 in it. So what I'm going to do is I'm going to add this to both sides. So I get x squared g squared over v0 squared cosine squared theta equals 2gy0 plus 2xg tangent of theta. Now I can multiply, I'm going to actually cross multiply. You can call it that. I hate saying that. Okay. I'm going to multiply both sides by v0 squared and divide both sides by this. So I get x squared g squared over cosine squared theta times 1 over 2gy0 plus 2xg, that's a g, tangent theta equals v0 squared. So now I just have to take the square root of both sides, and I get v0 equals, well, this stuff's easy, right? I have xg over cosine theta, and then I have 1 over the square root of all this stuff. So the square root of 2gy0 plus 2xg tangent theta. If I want to factor out the 2g, I could, but I didn't. But that's it. So everything on this side is something I measure. I measured theta. I didn't measure g. I know g. I measure x. That's how the distance it went. That's the starting position. Then starting height. That's g again. Xg. Okay, but let's just double check that the units all work out, because if we can do one thing, we can check the units. We could change. I'm not going to do it, but you could take the case where theta is 0, because we've done that equation before. I can do that actually. So this g, let's use the units of g in meters per second squared. So if I multiply meters by meters per second squared, this gives me meters squared per second squared, because cosine theta has no units. So it's meters squared per second squared for this. This term right here, these two terms have to have the same thing. Meters per second squared times meters. So I get another meter squared per second squared. And this too, meter squared per second squared. So the whole term here is meters squared per second squared. When I take the square root of that, I get meters per second. And then when I divide meters squared per second squared by meters per second, I get meters per second. So it at least has the right units. Okay, that doesn't mean it's right, but at least has the right units. So now what we're going to do is, what I'm going to do is collect data. I'm going to record the y should be the same. I want to keep the y0 the same. So I need y0 equals some value. I did measure that. And then how far did it go, and at what angle did I launch it? And I can use that to calculate the velocity, v0. And then I want to plot v0 versus theta and see if the velocity changes significantly as I launch it up. I would expect that the velocity would decrease as I launch it higher, but we'll just have to check. Okay. So let's look at the data. Switching to the data. Switching now. I don't need this anymore. I need this. Okay, so I entered this into a spreadsheet right here. So this is, I had the two launchers. I had the small launcher and the large launcher. I recorded the angle in degrees. I record the x. This is the mass. This is the ds is the distance it compressed. I want to measure the spring constant. I didn't do that. I need the mass and how much the spring was compressed for each one. I do need the y0, and that's in centimeters. This is in meters. Yeah. So let's put this at. Did I write that anywhere else? Okay, let's put y0 as 0.128. I'm going to do this one first. So I want to calculate v0. So I can use, all I need to do is type in this equation, this nasty equation, into the spreadsheet, which I don't really like to do, okay? But I'm going to do it anyway. So let's see if I can pull this down so you can, you'll be able to see it. Okay. So I'm going to start typing. It's going to be x times g, so I need g. I'll just type, I'll just type it as 9.8. Is that okay? Okay, so it's going to be x, so it's going to be this value, times g, times 9.8, divided by cosine theta, so cosine in radians. So it's going to be cosine of this times pi divided by 180. That's cosine. I wonder how you do that cosine function in degrees, because that looks messy, but whatever. Okay, so I'm going to put this in parentheses up here just to make sure that my order of operations is legit. This. Times 1 divided by the square root of 2 times 9.8 times y0. So this is my y0, and I'm going to go ahead and put a $sign there because I don't want that number to change. Okay. Plus 2 times x, that's my x, times g, 9.8, times tangent of theta, and then I have to say multiply by pi, divided by 180, which I'm sure I don't have to do that. And someone try watching this like, you are not listening. You do not have to do that. Okay. And then that's that. And if I press return, will there be an error? Okay. There's not. Okay. So it seemed to work. Let's do this other big launcher, and then we'll plot these two. So the big launcher has a y0. Let's put this as 0.246. I'm going to just copy this down here. Now, I do need to change some stuff because I need, instead of, let's see, this one uses F2. I want to use F12. But other than that, everything's the same. So I just need to change F2 to 12. F2 to 12. I think that's it. And it wants to fill it. I love that autofill. And you'll see right there, it looks fairly constant. Let's go ahead and plot these things. I'm going to start with this one right here. So I want to plot theta. So this is how I'm going to use, just because I think it's really quick and I think it's a great plotter, I'm going to use Logger Pro. There is graphical analysis by Vernier, and I think they do, it's the same functionality for the most part. But I like Logger Pro. So I'm going to copy this. And I'm going to go to Logger Pro, which I already have open. Oops. That's not what I wanted to do. I want to move this. Okay, and let's make that a little bit bigger. Make it bigger. And I'm going to paste it right in here. And then I'm going to change. Oh, I don't need that. Well, that's fine. I don't think it'll plot that. I'm going to just delete that. Let's just delete the whole thing. I didn't do it. Okay, that's fine. I'm going to change the name to theta in degrees. I do like this about Logger Pro. I wish how do you make it bigger? Can you make view? If I can make the window bigger. What if I just do the normal trick of zooming in? No? Okay. Now I'm going to go back over here. I'm going to paste the velocity data. I'm not going to do the, I guess I should do the other one. And I'm going to paste it right here. And then I'm going to say this is V0 big, V0 B. meters per second. Okay, so here it automatically made a graph of V0 versus theta, and you can see these points. They're very constant, much more constant than I would have thought. I could fit a line to that and see if there's a function, and oh, they only fit to those two. And there is a slight increase in that, which is because these down here. Wait, what was that? Theta. Okay, that just shows there's no real pattern, right? Because these go down, the velocity goes down with angle, and then up here it doesn't. I wonder if my initial position changed significantly as I moved that thing up. I try not to make it, but it's possible that it could have. I did not do a careful experiment. I thought it'd be clear and obviously different velocities, so I just did it really quick. I mean, I would definitely repeat the measurement multiple times, get an uncertainty and all that stuff. I didn't do that. I really just wanted to focus on the calculation. Okay, so this gives me the slope and the intercept, the correlation. Let's do, where's the stats button? Yeah, it is. Okay, so this says the average is 2.266 with a standard deviation of 0.056. So that's not too bad. Let's say 2.26. I'm going to write it over here and I'll show you. V0 equals 2.266. I'll go ahead and write it out. Plus or minus 0.06 meters per second. That's not so bad. Okay, let's look at the other data. I can plot on the same graph. So let's see if I can take this. This is so small. Make that bigger. And then do insert data. New manual column. And let's call this data 2. Data 2 degrees. And then another new manual column, data, new manual column. And we'll call this V0, what do they call the other one? V0 small. And then V0S, meters per second. Okay. And then over here, I'm going to, I didn't do as many. You'll notice I only did launch angles from 0 to 45 because that smaller one, it was hitting the bottom. I couldn't get it up steep without messing things up. And I told you, I was just trying to, I thought it'd be so obvious in my impatience. So there's my thetas. Let's paste that right here. I don't know why I put it down there. And then let's go to get the V0s and paste that in here. And then I'm going to say V0 small, more. I can do more. I can do V0 big and V0 small. And then down here, I can do theta more. Theta I guess it's just theta. That's fine. But they're not the same angles. I guess what I have to do, let's do this. Yeah, I can't have two different axes there. So let's just, that one actually is 10. These are the ones that are different. So let's just copy these and put them down here. I know that's stupid. And then copy these and cut them and put them down here. There. And then do this. Okay, so get rid of these things. So there's my other data right there. And it also, you see it right there? It also seems fairly constant. I'm very impressed. So let's get the statistics for that. And small. Okay, so this has V0 equals an average of 3.21 plus or minus 0.05. So there we go. Okay, so let's switch back over to the paper so you can see that. So this is the launch velocity with standard deviation for the large ball launcher. This is for the small ball launcher. I mean, I think if I wonder about using a larger mass ball so that I could really see the difference in that spring, because it should change, right? And also, I only went up to an angle of 80. Oh, I did 80 degrees. So this is really kind of surprising. It went up such 80 degrees. But I guess if your compression distance is really small, then the amount it moves isn't that much. And I only did this on low setting. They have low, medium, high, and low ranges. So there's a whole bunch of experiments you could do this. It'd be a lot of fun to really go all in and collect data. But I don't have the patience because I like to make videos. So really, this is the thing I wanted to derive this equation. Calculate V0, launch from an angle off the table. And this is also why I have my students launch it horizontally, because this is kind of messy. But I hope that helps. I'll talk to you later.